Gnanam paramam dheyam. Knowledge is supreme.
So now I am going to slowly take you into understanding operators, which should also be categorically say that this is like a spin 0 operator or angular momentum 0 operator, angular momentum 1 operator and so on. So that is a very neat way in which you can see. One is a trivial operator, which is a scalar operator. When you call it as a scalar in classical mechanics, why do you call it as a scalar? You only look at rotations because angular momentum is a generator of rotation. Under rotation, a scalar operator remains same. Radial coordinate, for example, is actually a dot product of 2 r dot r vector under square root. That radial coordinate does not change under rotations, right? So that is why you call it as a scalar. Now we want to associate with such scalars operator. You can have a position operator, the radial operator in central force problems. So this radial coordinate operators are scalar operators is what we will say. But what is the formal definition? Under rotation, we have seen how state vectors transform, and we know we need to see how a linear operator transforms under rotation, any linear operator. So if the state vectors transform under rotations, you know how it transforms, e to the I j dot theta by h cross. The corresponding operators can transform this way. So when do we call an operator scalar? When a prime is equal to a, no change. When a prime becomes equal to a, we call it as a scalar operator. When can that happen? When can that happen? Only when the commutator of the scalar operator with angular momentum, this is 0. All of you have checked that the Li with r coordinate or function of r radial coordinate is 0. You have checked mechanically. Now I am just trying to say that scalar operators, they commute with angular momentum generator. That also tells you that the other operators will not commute with angular momentum generators. Right? When this changes, then they will not commute. Classical mechanics tells us that if you have a vector operator or a position vector, you know how the position components of that vector transform under rotations. All of you know. And any vector operator, like you take vector potential or electric field, momentum, they have to transform. Their transformation properties are not different from your components of your position vector, right? That is why you call them to be vectors. Even amongst the vectors, there are some more distinctions. What are the distinctions? Those which change under parity, those which doesn't change under parity, they are polar vectors, axial vectors. Let's not get into that. At least for proper rotations, there is no difference. And under proper rotations, any vector will transform like components of a position vector. This you know from classical mechanics. Clearly, this above equation, A prime is not A. You know how A prime changes also under rotation. From there you can deduce what is the commutator of angular momentum with different coordinates, position coordinates. Whatever I write for the components of the position operator, it should hold for any vector operator. I'm sure you would have checked this. If you have not, you should go back and check this. J, I with any dot product, that is 0. And you can also show that So this is why it is called as scalar operator. And Ji with Aj will be, if it is position coordinate, you know what it is. IH cross epsilon ijk ak. So this is what we call it as a vector operator. Okay, we call them to be vector operators if it behaves exactly similar to the way the components of your position vector behaves under rotations. So you can go and check that Ji with momentum J components, what it is. It will be IH cross epsilon ijk pk. Angular momentum, Ji itself is a vector operator. This satisfies your familiar angular momentum algebra. You know how the components of your position vector changes. We did this also, delta r. Do that the same way, delta A will also change under rotations. And if you try to write that out, you will find that the commutator bracket of that, because delta r, if you remember, it's delta omega cross r for infinitesimal rotation. Do that for any delta of a vector operator. If you do that, if you compare both sides, the only way both sides can match is if this commutator, keep this theta to be small, there will be a commutator bracket, and that commutator you can show it to be. Exercise for you, practice exercise. I did this elaborately for position operator. Please go and do the same thing for any vector operator. Any vector operator should behave exactly same like a position operator. So this is a vector operator, this is a vector operator, this is a vector operator. They all transform. Whatever is a vector operator should be seen on the right hand side. And what is the next operator we should consider? We did scalar, we did vector, then we should look at tensors. One of the familiar tensors which you have all studied is the moment of inertia tensor. Moment of inertia tensor has two indices, right? Sure, you have all done also in the lab, working out moment of inertia. Also, a lot of problems you have done on moment of inertia. It's a matrix. That much you know. It's a matrix. With matrix can be written as some Mij matrix or Iij matrix. Whereas a vector has only one index. A scalar has 0 index. Okay. So I am just slowly, gradually taking you to the concept of the behavior of different operators under rotations are different. If you take the moment of inertia with two indices, if you do rotations, what happens to it is what I want you to go and look it up. If you take Iij, I am sure you would have all done this, but in case you have not done this, let me just. So if I take Aibj and call this to be a Tij. So moment of inertia tensor, this one, let me write it as M, Ri, Rj, let me forget about all those subtraction and so on. Just for example, if I take this, A and B are same. Allowed? When I do a rotation on a two indexed object, when I do a rotation on a one indexed object, I will get A prime I to be Rij, it's a rotation matrix, times Aj. When I do it on I prime Ij, or let's even take T prime Ij, under rotation what happens? Ri I1, Rj J1, similarly this one also, it's the same R matrix, How many elements are there in 3 dimension? How many are there? 9. Okay. If I look this up as a vector, Ri as a vector operator, how many components it has? 3 components. This is another vector with 3 components. Combining 2 vectors is like taking tensor product. Okay. So I have combined 2 vectors. This also combined 2 vectors. This is a vector. This is a vector. This vector has 3 components. This has 3 components. Combining is a tensor product. What is the dimension of this composition? 3 into 3. There are 9 independent components, you said. 9 independent components of the composed object is made of 3-dimensional vector multiplied by 3-dimensional another vector. Does this ring you a bell? Something what I am trying to drive at? We did uncoupled basis and coupled basis in the context of states. I can also compose operators, take 2 vector operators and compose them and get a 2-indexed object, and now I would like to resolve. So this is uncoupled. Okay, I would like to resolve this into pieces which I will call it to be like similar to your coupled case. One is trace of T matrix. What does trace of T matrix do under rotations? Trace remains invariant under similarity transmission. The trace of T matrix is behaving like a scalar under rotation. It is 1-dimensional. This is 1-dimensional. What else can I do? I can take a cross product of these 2 vectors. Cross product of 2 vectors in 3 dimension is a vector, right? A cross B is a vector. So I could write an antisymmetric combination which I will call it as A cross B. How many components are there? 3. A cross B has only 3 components, right? Antisymmetric. T12, T13 and T23, and the others are antisymmetric. 3 components. But that will behave like a, under rotation it will behave like a vector. What is left? I pulled out a trace. I pulled out an antisymmetric operator. What is left? Symmetric I have not taken it out. Symmetric, and you have to subtract the trace. Okay, so that is the symmetric will be how many components in 3 dimension? Symmetric matrix. And if you remove the trace, trace is one condition. One condition. You are not removing the diagonal elements. So 5. So 5 components, 5-dimensional state in your angular momentum is called what? J equal to 2, right? J equal to 2 is 2j plus 1, which is, so there is some resemblance here. What did I do? I got a composition as a raw which is 9-dimensional. I would like to pull out a piece which is invariant under rotation, which is a lower dimensional one. Another piece which is invariant under, it's not invariant, it is behaving like a vector under rotation. And then the other one is j equal to 2. So these are j equal to 1 and j equal to 1 because they have 3 components. When you combine two operators of j equal to 1 and j equal to 1. What are the possibilities we saw in angular momentum combination? You have to get j equal to 1, j equal to 2, j equal to 0. That's exactly what I get. But I have not really done the algebra for you. I just gave you some kind of a feel. So, all the operators, of course, all the operators are going to have only integer angular momentum. Let's put it that way. Okay, all my vector operators, physical momentum, angular position, momentum operator, everything is, these are all integers. Yeah, so I should call this to be technically as L if you want, because it has three components and it is a vector operator. The number of components, it's an analogy, or there is a one-to-one correspondence between operators also to behave the way we did the Clebsch-Gordan matrix. Okay, this is just for you to think about it. All your spherical harmonics which you did, all your spherical harmonics, you never wrote it as, you never took quadratics. If you remember, we did this. We said we can write all polynomials in variable x, and in 3 dimension also you could do that, but that's not what you took. You took a linear combination in r theta phi, especially theta phi, in a way that you can call L equal to 1, L equal to 2. Remember the way you did this. You never took. So I am just trying to kind of give you a feel that there is some kind of an one-to-one correspondence that you have a state Jm. There is an equivalent way in which you can say the operators with one index, which I will call it as k, and the other index which I will call it as q. So, scalar operator is 0, 0. Vector operator is 1, q, which has 3 components. This has 1 component. And the next thing is, you can compose vectors to get the higher rank tensors. Can compose vectors, can compose 3 vectors to get a third rank tensor. Whatever I did today is AI, Bj, but you can take AI, Bj, Ck and can get a 3 indexed object. Okay. So, we will go to this tensor operators in the next lecture and see that the composition, if you combine 2 spin j's, how things happen, will also happen in this case. The same CG coefficient will help you to resolve. Okay, let me stop here.